Hello, everyone. Thanks for joining us as the chair of the Scientific Council of ISNAF, the Italian Scientists and Scholars in North America Foundation. It's my great pleasure to welcome you to this final for the ISNAF Embassy of Italy Award for Research in Quantum Technology. ISNAF annually presents the Young Investigator Awards to exceptional early career Italian researchers and scholars working in the United States and in Canada. These awards celebrate groundbreaking and impactful contributions across a range of academic disciplines. This final is for the Embassy of Italy. It is the Embassy of Italy Award that was established in 2020. And in this year's edition recognizes outstanding contributions from Italian scientists active in the broad field of quantum technologies, recognizing groundbreaking research that advances our understanding and application of materials, algorithms, and platforms for quantum computing, sensing, and imaging. I've been very honored to chair this award committee, and I want to thank the jury, Dr. Stefano Lami from the National Quantum Information Research Center, and Professor Alberto Salleo from the Stanford University. I also want to thank the other referees in the panel that selected the finalists, in particular Professor Massimo Ruzzeni from CU Boulder. Finally, I want to congratulate the finalists. The pool was particularly good this year. We had a very difficult time to select the three finalists, and we converged on Dr. Marco Colangelo, an assistant professor at Northeastern University, Dr. Gabriele Pasquale, a postdoctoral fellow at Harvard University, and Dr. Giovanni Scuri, a Bloch postdoctoral fellow at Stanford University. So now we will start with the presentations. The first presenter is Dr. Marco Colangelo, and this talk is on high-performance superconducting detectors for quantum information science applications. Marco, if you can, please share your screen.
Yes, thank you so much. 1 second, let me see. All right. All right, can you all see the slides? Perfect. All right, so okay, so thank you so much for the introduction. And yeah, so my name is Marco Colangelo. I am an assistant professor at Northeastern University, and actually my group does mostly research on applied superconductivity, and specifically on the device architectures and with applications in quantum information science. And today I'm mostly gonna focus on the superconducting detectors and also try to convey why do we need them and why specifically do we need them to get in high performance. So before that, I kind of want to mention that I'm very amazed that this year Embassy of Italy Award sort of like matches the same topic of the 2025 Nobel Prize in Physics that, as we know, was given to Clark, Devoret, and Martinez for, among the other things, the discovery of energy quantization in electric circuit, which, as we know, is sort of like the basics for one of the flavors of quantum computing, specifically the superconducting qubit type quantum computing, which is nowadays used by IBM, Google, and many more. So beyond this, beyond this sort of like single computational platform, the vision here for the community is actually to build a global quantum internet where we could actually take a computing node in a certain country from a certain company and a computing node in another country from another company and potentially connect them and exchange quantum information between them. And this is actually a very challenging task because we need to sort of conserve coherence and like make sure that the information is not degraded. And this is done to transducers, which convert the several type of qubits into photonic flying qubits that then are sent, so to photons basically, that then are sent to a photonic link made of like optical fibers, for example, and where the information is actually every once in a while detected and exchanged and processed, etc. So in these photonic links and also in the transducer, we kind of need several tens, hundreds of single photon detectors. And really the requirement is that we really do need good single photon detectors. So what does good means? So good clearly, if we actually sort of like address these detectors from the traditional metrics, really means high efficiency, low jitter, low dark counts, high count rate. So these are sort of like the traditional metrics, which really need to be boosted to make sure that we keep the error low. We are able to enact long distance 𝐞𝐬𝐞𝐅 protocols and also heralding. However, we also do have new requirements that comes from novel sort of like protocols. So we do need our detector to be photon number resolving, potentially polarization resolving, and also mid-IR compatible. And these sort of address the new requirements from high performance protocols. For example, ultra fast time beam photon counting, and also the standard sort of like linear optical quantum computing KLM protocol does require photon number resolving detectors, which are sort of like very hard to come by. So now the question is that, do we have all of these? So the answer is no, clearly. Otherwise, we would not be here. However, we do have something really good, which are known to be the superconducting nanowire single photon detectors, or the SNSPDs, which are the detector of choice for most of the quantum information science applications. These are based on superconducting nanowires, where I enabled the pointer, where the nanowire is actually meandered in this 10 micron by 10 micron active area, and a optical fiber spot is projected onto the active area, and a single photon generates a output electrical pulse. So they're based on nanowires, so they do require nanofabrication technology. And the real thing is that this detector operate with a highly nonlinear mechanism, which makes them very easy to read out. Now, the nanowire is 5 to 10 nanometer thick, 50 to 100 nanometer wide, and it's made of type 2 superconductors, for example, niobium nitride or niobium titanium nitride, which has a critical temperature between 5 to 10 Kelvin. So effectively, this is a cryotechnology that needs to be cooled down. Now, the working principle is really amazing. So we do have a superconducting nanowire. It is in a superconducting state. So when we flow current through the nanowire, we have no resistive drop, so we have no voltage. When a photon comes, breaks the superconductivity and generates a resistive region that then expands across the nanowire. This resistive region is between 500 to 1 kilo. And so this resistive region pushes out the current to the load, and then sort of like this generates this traditional pulse that we kind of like associate to a photon being counted. And then after a relaxation, the nanowire is ready to detect again. Now, these are really, really amazing detectors. So they're the best detection technology for telecom and near-IR photons. And it's sort of easy to claim. So here, I really like to show these plots where we have 4 detection metrics: the efficiency, the jitter, the dark counts, and the count rate. And these numbers here, not very important, but they're kind of like the record for each of these metrics. And I also want to mention that the jitter and the dark count record metric are actually from my own research. And we can see that the SNSPD sort of like cover the full area of this plot and sort of beats on all the metrics, all the competing technology in this area. For example, the SPAD, the transition edge sensor, and the silicon photomultiplier. The problem with this plot, something that I sort of never mentioned, but the talk is about this, so it's important to mention, is that this is a lie. So this sort of like plot sort of like convinces and gives the idea that this SNSPD can get in a single design all of these very high performance, but that's not really the case. So we do have trade-offs between all of these metrics, and there are some important trade-offs, for example, between the efficiency and the jitter, where we get a mediocre detector if we try to get sort of like in between. We can maximize for efficiency or jitter, but never both at the same time. And this is a problem because the new requirements for protocols do actually need this detector. So how do we actually solve these intrinsic trade-offs? So that was sort of like my initial research. And I kind of like, we can see that this problem is actually given by some issues with the superconductor being a superconductor. So we do have the kinetic inductance, which is an inductive contribution of the superconductor given by the inertia of the Cooper pairs, and it's about 1 nanohenry per micron. Now, this number maybe doesn't say anything, but it's actually 1,000 times larger than the standard geometric inductance in this structure. So what happens really is that when we actually treat a nanowire, we are actually dealing with a microwave architecture. We're actually dealing with a microstrip when we have our nanowire reference to maybe a ground, which is the back reflector of the optical cavity. So now if we plug in these numbers here, this 1 nanometer per micron, and also calculate the capacitance between the nanowire and the ground plane, we do realize that the effective index is actually about 100 times 100. The impedance is 1 kilo, and the speed of light into the structure is 1% of the speed of light in vacuum. So these nanowires do behave as a slow speed transmission line with a high impedance and extreme wavelength compression. That's very nice because we can actually do fancy things with this nanowire, and this is part of like my broader research. However, they are a big problem and a culprit in the trade-offs of the detector, because high impedance means that when we interface that to the 50 ohm, we have reflections and there is no escape from that. And this slow speed of propagation means that we do have pulse propagation delays into the area when we use this detector. So now, how do we solve this problem? And here, to just like show you the trade-off, we take a 20 micron by 20 micron area detector, and we try to make a very large detector because we want to maximize the collection efficiency. So we want to have a very high efficiency. And this detector is actually referenced to a gold ground plane because it's embedded in an optical cavity. Now, we assume that our projected fiber spot do generate like 3 hotspots, so we have 3 photon detection, and we can see that one is very close to the ground, while one is very close to the readout. So here, if we actually take the slow speed of the nanowire, 1% of c, the round trip time from the ground to the readout is actually 300 picoseconds. So it means that the output pulses corresponding to the yellow, for example, photon and the blue photon actually will appear at the readout with a certain delay, which is intrinsic to the active area of the detector. And there is no escape from that. This is called the geometric contribution to the jitter. And this really creates a problem because we really do want a large detector for active area, but at the same time, a large detector will mean a very high jitter. And so we're actually playing this trade-off game here, where, for example, the record efficiency detector at 98% had a terrible jitter of 400 picosecond, while the very good detector jitter at like 4.5 picosecond had a terrible efficiency. So we are playing this game. Now, is there a way to beat the game? So there is, and I introduce you what's called the impedance match differential SNSPD, which is something that I've done during my PhD. So this is a revised architecture of the SNSPD. You can see that this is actually a picture of the real device. So this is a lollipop-shaped die, and it's lollipop-shaped because we use it for like self-aligned coupling. So we basically project, and so this is basically the same diameter of a ferrule of an optical fiber, and it's self-aligned because the mode is directly projected onto the area of the SNSPD through the optical cavity. But the real difference here is that we do have monolithic impedance matching tapers that allow us to solve the impedance matching problem. And we also do have differential readout, which allow us to play a little bit of game in signal processing and sort of compensate for this geometric jitter. So when we do test this device, we made a few actually. This is a standard sort of like way to characterize the efficiency. You typically plot it as a function of the bias current. Here we test 4 devices from the smallest to the larger, D2A, and we can see that the efficiency does increase from 8% to 85% following the area. This makes sense because larger detector, larger efficiency, and our maximum efficiency is actually at 85% due to some small issues with the optical design, but nothing intrinsic to the detector really. The big deal is that when we do test instead the jitter, each device design do converge below 15 picoseconds. So independently on the large area, we are getting more or less the same number of picoseconds in the jitter, around 12 to 13, meaning that our differential design and impedance matching design is actually working to compensate for these intrinsic issues. And most importantly, when we do test the 775 nanometer, we do break the 10 picosecond barrier, which was believed to be sort of impossible for large area device. So this is still an unbeaten record in the community. And so we're able to basically merge in the same design a very high efficiency and a very low jitter, which is very good for all the protocols requiring high performance. Now, this detector, thanks to the design, they also have imaging capabilities, which is a little bit long to explain, but basically the core is that we are able to understand if the mode that we couple onto the active area of the device is actually misaligned from the center. And we do that by analyzing the output distribution of the pulse histograms. And as you can see here, for example, this distribution is actually misaligned from the center, which is an indication that there is a delta Y misalignment through some processing. And I want to mention that each of these tiny Gaussians inside of this largest distribution corresponds to the detection in each single wire of the meander. So we do actually have maximum resolution in trying to understand where the photon actually falls and hit on the nanowire. This is something that it's impossible in standard devices. The other kind of like impossible things before was actually the photon number resolution. So our detector also encodes the number of photon into an optical packet into the amplitude of the signal. And with some signal processing, we are actually able to actually claim a photon number resolution in these devices. And this is the first time for single photon detectors in the SNSPD flavors for this type of application. So we do have a device that is able to get high efficiency, low jitter, imaging capabilities, and photon number resolution in an all-rounder approach and technology for quantum information science. On top of that, if, for example, we also need to maybe apply this detector in mid-IR, for example, for covert quantum communication, this detector is also able to detect mid-IR photon at 7.4 micron in large area SNSPDs, which is one of the first sort of like record and one of the first time this is actually shown in a device like that. So with this improvement in the design and technology, we're able to get a device which basically breaks most of the trade-offs for SNSPDs and propose a detection technology which is super useful for all of the applications in quantum information science that relies on detecting photons. The only problem is that they are not photonic integrated, so it's free space. So how do we solve this problem? So by using more or less the same approach of differential readout, impedance matching, we can actually fabricate this device on top of an optical waveguide. So instead of relying on projecting a beam through an optical fiber, we do pattern the SNSPD on top of the optical waveguide in intimate contact and leverage the mode leakage on top of the waveguide to do the detection. And so here it's a demonstration on lithium niobate, which is a promising platform for photonic applications. And by testing again the efficiency and the jitter, we are able to get 50%, which is actually a record, again, on efficiency on lithium niobate for this type of integrated devices. Another problem of this approach is that this is one device. However, we said at the beginning that we will need tens and hundreds of the device. So I'm showing here, sort of for the first time, a interesting plot where we do see a sort of differential signal. We have a negative pulse, a positive pulse. We are triggering on a negative pulse. And as you can see, you can actually count 65 groups in that positive pulse, which basically gives back a detection in 65 channels, which are time multiplexed. So this is a SNSPD fabricated onto a SOI platform where we do have 65 channels all spaced together in a time multiplex approach. And it's the largest monolithic integrated array ever fabricated. And specifically, again, the device is a little bit complex, but it's on a SOI platform. We have the tapers here. It's in a differential readout. And each device is actually spaced by each device is coupled onto a waveguide and it's spaced by a monolithic delay line. And the device actually takes some input with grating couplers, and then there is a processing area. This is specifically a 3 to 65 coupler that basically performs boson sampling on chip. And I want to conclude by saying that my group is also pushing a little bit further with the optical engineering by implementing plasmonic enhanced nanowire. Instead of using linear wires, we use fractal curves to be able to extend the broadband sensitivity of our wire. You can see from like 2 to 7 micron flat. And we're also working in making polarization encoding by optimizing the absorption of the TE versus the TM mode, where the nanowire is actually placing here instead of the cavity. So this was an overview of what we do for high performance detectors for quantum information science. Thank you so much for your attention. And of course, I have to acknowledge a lot of collaborators, a lot of funding, And also, this is my my students at Northeastern Universities for the amazing work. And thank you so much.
Thank you. Thanks, Marco.
Thanks.
We have about 4 minutes for questions. Stefano or Alberto?
Yeah,
You
no, I
ready?
would like to congratulate. It's very good presentation, very clear, and clearly of a high significance to the field. I mean, also my research center, we are working on transduction for photonic links. So I would like to understand better your individual contribution, your role in the field. I mean, compared to other teams. So can I assume that your breakthrough is this impedance match differential SN-SPD that you also cited, this article on Physical Review Applied, and what is next?
Yeah. So, yeah, perfect. So yes, actually, I don't know, most probably I still have my slides on, but yeah, so this architecture, it's something that come out directly from actually my PhD work, and then my, let me actually go to, there we go. So this is actually the sort of like my grad school work, sort of like my achievement from grad school. But what I'm doing in my group right now is taking these initial design that was done, that I basically did in grad school, and try to do even better and even better. So sort of like refine a little bit all the photonic, all the issues with the optical coupling, make sure that we're able to really to get to 99% efficiency and very low jitter, and also most probably going toward photonic integration. So basically take this free space coupled approach and go to the all full photonic integration, because that's kind of like where we are going, and that's also solve some of the scalability issues, because clearly this is a free space coupled device, so it needs sort of like researcher to actually put the fiber in. While if we do pattern a photonic integrated device with 100 channels, 200 channels, we can just use sort of like a fiber array one time, and it's basically done. So it's kind of like going and try to solve the scalability issues of this technology. Once the detector is there, once the sort of performance are there, we do need to address the scalability issues. So that's what I'm doing in my group right now.
Thank you.
Thank you. Congratulations.
Marco, I had one question. The idea of using differential readout and impedance matched resonances, it's pretty established in microwave engineering. So the challenge here is to translate this into a superconducting platform with the challenges in fabrication.
Exactly. So yeah, go ahead. Sorry. Sorry.
No, so I wanted to understand what is actually the lead breakthrough that you are working on. I was also curious about your plasmonic approach you were mentioning and how that comes in.
So as you said, of course, like impedance matching has been around since basically microwave engineering exists, sort of, and the differential readout is also a used technique. So the problem here was to like the first blip was to understand that the nanowire are actually transmission lines, and the problem is that also understand what is this kinetic inductance, because again, kinetic inductance is a known concept in superconductivity. However, the problem was are the nanowire actually affected by this kinetic inductance? Is it important in the nanowire? And it wasn't clear before. Now it's very clear, and it's also sort of like back demonstrated by the fact that by actually performing impedance matching and differential readout do help a lot with the performance. So the sort of initial breakthrough was we can buy SN-SPDs, no problem. We can actually pay 100K to companies and they ship it to us. The problem is that they are standard detectors without impedance matching, without differential readout, and they have this trade-off. So here we're actually breaking these trade-offs, and we provide to the community and also I mean, of course, this is a patented technology right now. We do provide to the community a way to actually break this trade-off and do even better on all the protocols and all the sort of like, quantum information operations that we might want to do. And for the plasmonic one, actually here we are trying to do something that it's a little bit challenging. So we are trying to merge the concept of like plasmonic enhancement of like optical fields. So we do excite plasmonic modes onto this nanowire. However, the nanowire, to make sure that it supports plasmonic mode and field enhancement, have to be shaped in these fractal curves, like space filling curves, to actually do generate the plasmonic mode. This is very challenging because it requires a very careful selection between the right material, which being right material is not exactly the best superconductor. So you kind of like need some trade-off between what's plasmonic versus what's superconducting, and trying to find like the material that works the best. And second is the fabrication, because each of those nanowires is 40 nanometers. So it's actually very challenging to fabricate. And we're trying to do it. It seems that we are getting there. And we are, again, trying to match and integrate the plasmonics with the superconductivity and trying to get some even better detector for mid-infrared application, both in the quantum information, but also potentially for space and exoplanet spectroscopy and all the devices that sort of like can help these disciplines.
Great. Thank you, Marco, for the great
Thank you.
presentation. I think we need to move on to the second
sorry.
finalist. Thank you. This is Dr. Gabriele Pasquale, postdoctoral fellow at Harvard, and the title of his presentation is Revealing and Controlling Quantum Matter for Next-Gen Devices.
All right. Can you see everything correctly?
Yes, perfect, yes.
Okay, thank you. Thank you very much for the introduction, and I am really honored to be selected among the finalists at the Embassy of Italy award. So first of all, I want to start from, I was thinking about this prize, and really honestly, this is different from any other prizes. So I was thinking, like, how can I define what for me means? What does it mean to be an Italian ambassador of science? And I kind of landed eventually thinking about this on this quote. So to me, Italy is synonymous with creativity, scientific genius, and warmth. And therefore, to be an ambassador of Italian science, to me, means to really embody these qualities that the world envies us and try to convey them through the work that we do. Therefore, through my work, I really want to share and show to the world that these values that we cheer in Italy are alive and thriving. And I want to bridge the Europe and the United States with Italy at the heart of this connection. And to really understand where I'm coming from with this statement, I really want to bring you briefly on an outline of my journey, which has been very international. And I think it really enriched the way I see the world, and therefore the way I pursue my scientific research. So I started in Venaria Reale in Torino, near Torino. And as many people from my hometown, I started my academic journey at Politecnico di Torino, where I studied engineering physics. And that really gave me a solid foundation to start pursuing my scientific career. And from there, I also got the first opportunity to do research abroad at KAUST in Saudi Arabia, where I had my first hands-on experience in a full-on English environment, which was really helpful. And that kind of pushed me to start studying abroad. So I moved to Sweden for my master's at KTH, also in engineering physics, where I started delving into nanoscience and nanotechnology. And eventually I landed on spintronics as a first topic of research. And that brought me to two subsequent research stays, first at the University of Cambridge and then at ETH in Zurich, where I also developed a lot of interest into spintronics and thin materials and optics in particular. And from there, I moved to Switzerland, to Lausanne in Switzerland at EPFL, where I did my PhD. And here I changed gears. So I discovered two-dimensional materials as a platform for science. And I thought they were really, really interesting. And therefore, I switched my research to two-dimensional materials, and in particular, in two-dimensional semiconductor and flatbed systems. And from there, that landed me here to Cambridge, working with Professor Philip Kim at Harvard University. And what I'm doing here is really to try to bridge my expertise in two-dimensional semiconductors with high-temperature two-dimensional superconductors, and try to discover new basic science with these materials and how they can be useful for future technologies. So that brings me to my scientific vision. really, my scientific goals are very broad. They entail quantum sensing and quantum technologies at the center, but not only. I would say my interest lies also in any kind of energy efficient hardware, and therefore also AI and other topics are of interest since they are very pressing for society these days. And I really think that to achieve all of these goals, especially today, I'll be talking about the quantum sensing and quantum technologies, we need two core ingredients. And one is that we need novel materials to discover new properties that can allow this new application to really thrive. And in this group, two-dimensional materials, I believe, hold a special place. And I've been spending the last couple of years investigating such platforms. And the second one is novel experimental probes. So we have already a lot of experimental probes, but learning how to combine them onto new material platforms, I think that really holds the key to open the door for new quantum applications. And when we really think about quantum technology and the backbone of quantum technology, we have to think about superconducting circuits like transmon, flux, qubits, and so on. And they're all based on Josephson junctions, microwave resonators, and there are many players in the field, some, for example, IBM and Google. But there are two things about this technology that I want you to focus on right now. And the first one is that they operate at millikelvin temperature, which is a very limiting factor and complicates a lot of the really applications that this kind of potential computing tools can have. And the second one is they strongly rely on superconductors. And even though we studied superconductors for many years, we actually don't really know how superconductivity really emerges in these systems. Even though we have some expertise, we still have a lot to figure out on that front. So let me start by the first point. So since they operate at millikelvin temperature, I think one of the first questions is that we need to ask ourselves, how does it work? How does thermal power conversion work at millikelvin temperatures? So how do we keep the system cold? And how, if we have some local heat happening in the system, how can we remove it from the circuit in a controllable way? So I did during my PhD, I did some research on exactly this topic, where we combined two-dimensional semiconductor indium selenide with graphene, and we built a thermoelectric device, which basically does thermal power conversion under magnetic field. And what we have seen is that it can be the thermal power, so the efficiency of conversion can be controlled by gate voltage and can be increased by 3 orders of magnitude electrically, some sort of transistor, if you wish. So what this means is that we can control locally with a nanoscale device, how do we translate heat into currents and vice versa. So this is very interesting, and we can think about the device performance of such a device. And when we decided to quantify this, we had to compare first to the literature, the electrical performance, which turns out to be very good, but also the thermal power conversion performance, which not only is record high for those ultra low temperatures, I'm talking around 100 millikelvin, but it can be largely tuned with electric field. And therefore, the point I'm trying to make is that novel materials are really at the core of this innovation. We cannot decouple a tool that we are using now as a quantum cooling device from the two-dimensional materials that are really at the backbone of this discovery. So this was where I started with the quantum computing avenue, but then I started thinking about, okay, but then how about superconductors? What do we know about them, and is there a way we can find out anything further? So on this front, when you think about superconductivity, we cannot not think about cuprates, in particular BISCO and YBCO, which really defined heavily their superconductivity research in the last decades. They have this very beautiful phase diagram, and they have a lot of phases which are to this date not well understood. However, the research in cuprates kind of hit a plateau in the last decade, and the reason is that trying to understand superconductivity in such complicated systems, it turns out it's really hard. You have very different atoms, very different compounds, and a lot of difficulties into the fabrication. To make different dopings, you need to make separate devices, and that really complicates things. However, superconductivity really witnessed a revival in 2018 when 2D materials entered the game. So it turns out that if you twist 2 layers of graphene, to a specific angle, which is called magic angle, you recover a superconductivity transition. And not only you have superconductivity, but you can control the different phases with gate voltage. And with that, you can sort of reconstruct the phase diagram of cuprates, but this time in a single device, only controlled by gate voltage. So this was really a very interesting discovery with two-dimensional materials, and it kind of opened the door to many further experiments. However, now we should ask the question, now we have only graphene. So now we have only carbon atoms in this system. So how does really superconductivity emerge in a material which is way simpler than the cuprates? And it turns out that the current most accepted theory is that superconductivity in this material emerges because flat bands emerge. So upon twisting, the band structure of graphene kind of merges. And as you hit the magic angle, then this flat band dispersion forms and the superconductivity can emerge. And we can think of it in the sense that if you have a flat band dispersion, at that energy, that directly translates into a peak of density of states, which is called Van Hove singularity. And Van Hove singularities combined with electron-electron interactions can give rise to instabilities and phase transitions such as superconductivity. So far, so good. However, there is a problem, which is that these flat bands are extremely hard to detect experimentally. Usually, it's something that you detect after many months of measurements, and you realize that you have a phase transition. So the question that I want to ask is there a way to detect experimentally in a quick and reliable way where these flat bands are in the energy diagram, and then use them for discoveries? So the work I'm going to talk about now is the first electrical detection of flat bands, which is something that we did in two-dimensional electrostructures based on semiconductors, flat band semiconductor indium selenide. And we saw some hints of flat band physics from photoluminescence, where we observed that at the whole conduction, so at the valence band edge of this material where the flat band is located, we see a strong quenching of the photoluminescence and a strong redshift, which is linked to the high effective mass of carriers at the flat band. But later, we decided to focus on out-of-plane tunneling currents, which turns out to be an extremely valuable tool for this purpose. So when I say out-of-plane tunneling currents, I really mean currents that goes from the indium selenide through the HBN to the backgate of graphene. So when we look at the in-plane transport in black compared to the out-of-plane tunneling current in yellow, we really see that at the whole side where the flat band is located, the transport doesn't really show anything meaningful. However, the tunneling current, and in this case, tunneling photocurrent, shows a very sharp increase at a very specific point. And we did a full analysis where we show that if you plot this tunneling current in the Simon scale, you're left with the trend of the tunneling mechanisms. And what we see is that there is a sharp change in tunneling mechanism that happens at a specific point. And we went on to demonstrate that this point is exactly the flat band position. So what we have is really a method that just with a quick gate sweep can locate a flat band in your field effect device. And we have defined a whole set of, let's say, rules, guidelines to generalize this effect to potentially any flat band system. And we have provided a guideline, but I want you to focus on is really the fact that the reason why this method works so well is because it entails 3 different exponentials in the formulas. So the current that you go to measure is exponentially dependent on the density of states through the effective mass, on the energy barrier between the dielectric, and the thickness of the dielectric. So what that means is that you can really play with 3 different degrees of freedom to enhance the signal that you have, which will be proportional to the density of states, which is naturally something you want when you want to study flat band systems. So now the question is, can we use this method to really probe new physics in this system? And to this point, the answer is yes. So we studied chirality to spin coupling in this 2-dimensional semiconductor. And what we have seen is that we have performed the first electrical detection of light chirality in an originally a chiral system. And we split this degeneracy using a magnetic field, where at 5 Tesla, for example, you can see that the currents blue and yellow, there is a strong difference in current by just changing the light chirality. So in other words, that means that with every parameter fixed, as we change the light chirality, we have a differential tunneling conductance that appears due to some intrinsic reasons in the material, which I don't have time to enter into the details, but it is linked to the fact that there is some spin polarization happening. And the point is that not only we could do this electrical detection, but we could use this to demonstrate a spin polarization detection in a flatband semiconductor, which was predicted around 10 years ago, and really remained elusive for a long time because of the very tiny magnitude of this effect, which is extremely hard to detect. And this tool, this method really provided us the opportunity to detect this spin polarization in the system. So going back to the scientific vision, now I really want to stress that after all these findings, I wanted to try to put together novel materials and novel experimental probes to push it towards the quantum sensing and quantum technologies angle. So the question is now, what can we do about two-dimensional superconductors, which exist because BISCO, for example, is a cuprate, but it can also be exfoliated down to monolayer. It turns out it's a van der Waals material. So therefore, now what we aim to do is to really make the first two-dimensional high-temperature hybrid super semi device, combining BISCO with two-dimensional semiconductors. Now, it sounds really good in theory. However, there is a very large limitation, which is that BISCO degrades at room temperature, in air, and with moisture. Therefore, what this means is that we need to have a complete stacking and fab process that happens at liquid nitrogen temperatures. And to this date, there is no fab that can be done in such conditions for these materials. So in the last year or so, I really focused my efforts into developing such a technique, and we have currently developed a technique that makes with which we can fab this kind of hybrid heterostructures. And we are currently at the point where we can make devices that show superconducting transition. Therefore, the BISCO does not degrade sizably in the system. And we can now study the properties of these hybrid structures. For example, through the optical spectrum, which shows already some interesting features. And we can combine all the probes that I have developed so far into this platform and try to achieve the first two-dimensional high-temperature structures for quantum applications. So really, when we think about the future work that I'm planning to pursue, I just want to achieve basically I want to combine the probes that I've developed with other probes that are already available in the quantum community and see how we can push those to explore further high-temperature quantum technologies. And in particular, one pressing question I have in the basic science side is to demonstrate optical detection of superconductivity in two-dimensional heterostructures. And to do that, we really need new material platforms. In particular, I think 2D hybrid super semi-structures hold a special place in there. And second, we also need new probes. So we need to combine quantum tunneling, optics, and microwave technology in a single platform to try to explore these future technologies. So with that, I would like to thank you all for your attention and all the people that made this possible in different groups and the funding agencies, in particular the Swiss National Science Foundation, which funds my postdoc in these times of uncertainty. Thank you so much.
Thank you, Gabriele. Great presentation. We have time for a couple of questions. Alberto or Stefan?
I'll start. Yeah.
Yes.
Thanks, Gabriele, for a great presentation. From one of your last slides, it looks like you're working with exfoliated materials. Is that correct?
Yes. Yes.
What is your opinion on a path towards something that is more scalable? Are these materials processable with more conventional deposition technologies?
Yeah, so it is a great question. So first of all, I want to mention that there are actually now companies emerging that are trying to scale exfoliation, which is also something that is quite interesting and quite new. So I don't know if they will succeed, but that is already something that people have been thinking about. But anyway, the point I want to make is that both BISCO and in TMDs, for example, can be grown even in the monolayer regime. So I think growth is definitely a path forward. Currently, we still are at the stage where the defect states and there are some other features that can be improved. But honestly, the progress has been very fast on this regard. So 3 years ago, I would have had a much more skeptic take on this, but actually looking at the speed at which they're improving, I think in a couple of years, in a few years maybe, we will be at the stage where we can grow full scale monolayers with very good quality and try to integrate them in these platforms. So when it comes to the BISCO integration, I think there we really need to ask ourselves what kind of applications we want to target. For some, we really need wafer scale. For others, we just need, let's say, small pixels, which potentially we can do in micro scale devices. However, I think that the method that we've developed is still compatible with large scale materials. So even though we're very far from that to demonstrate it ourselves, I think that's also an avenue of research. Yeah. But definitely growth is the way to go.
Thank you.
I don't know if Stefano has any, otherwise I will ask. Gabriele, great work. I was wondering, you are focusing on these new material platforms that can help us, or I guess geometrically, these twisting aspects that can somehow control the quantum properties of the materials. How far do you feel this to be to really impact quantum technologies? You talked in the last slides on this very interesting kind of spin momentum sensing, but can you comment a bit on the distance between this and an actual practical implementation for an application of quantum technologies?
Yes, so it is a great question. So first of all, I think twist angle engineering, the real impact of that was, this is my personal take on it. I don't think it will really be the game changer for the applications. However, what it really did, which I think is really something meaningful, is that it allowed us to understand another degree of freedom that allowed us to see new parts of how superconductivity emerges. For example, in this case, the twist angle creates flat bands, and flat bands give us superconductivity. So I think the main impact of that discovery is really just giving us a completely new game that we can play to understand how superconductivity emerges. When it comes to applications, I think that first of all, flat bands are not only in twist angle materials, they can be found in other materials. So I think the question we should ask ourselves is really, how do we induce flat bands, and how do we induce electron-electron interactions in systems that can do this at higher scale? So one of the I think promising avenues that we can have is that twist angle materials are still not out of the game, because graphene has this Dirac cone, which means that the angle you need to hit to get superconductivity needs to be extremely specific. With TMDs, they have more flatter dispersion, and the angle requirements are a little bit relaxed. So we can think of a system where we have a band structure which is way flatter to start with, and those in principle can give us superconductivity at way higher temperature scales. So as soon as we can reach the liquid nitrogen temperature, I think there might be some game to play there. So I think we're still at the stage of basic research on the twist angle for quantum, but we might not be too far, in the sense that the moment we can start with ingredients that are promising, there are already several theoretical proposals on how to reach superconductivity or emergent correlative states at temperatures even above liquid nitrogen.
Thank you. It's time to move to the last finalist. Thank you again, Gabriele. Dr. Giovanni Scuri, who is a Bloch postdoctoral fellow at Stanford University. The title of his talk is Integrated Quantum Photonic Devices for Sensing, Networking, and Information Processing.
Thank you. Okay, hopefully everyone can see the screen. Thank you so much for the introduction, and I'd also like to thank the entire committee for giving me this opportunity to discuss some of my recent research, specifically in making photonic devices for a broad range of quantum applications. Before I delve into kind of the technical details of my talk, I'll just say a few words of how I got here. I was born in Milan, and I lived there until the end of high school. And then I actually moved to the United States for college. I got my bachelor's at Columbia, where I started doing physics research actually in the field of 2D materials. And I continued researching 2D materials, generally semiconducting 2D materials, in Hong Kong Park's group at Harvard for my PhD. And around 3 years ago, I made the move from East to West Coast to start my postdoc here at Stanford, where I work in Jelena Vučković's group on a lot of the topics I'll kind of be covering in today's talk. So when we talk about quantum technologies, what we're really talking about is how can we use quantum mechanical principles, including superposition, entanglement, and state collapse upon measurement, to create devices that can outperform current state-of-the-art devices in sensing, networking, and compute. And you can think of, for example, using qubits in materials or atomic-based qubits to sense minuscule electric or magnetic fields that you can use for biological samples, for nanoscale NMR, or even for things like inertial sensors that all take advantage of these kind of properties here. You can think of making quantum networks, either long-scale quantum networks or even shorter-scale quantum networks, where you're able to distinguish whether there is an eavesdropper somewhere along the way, or you're able to connect multiple quantum processors with one another to try and scale computing processors to larger and larger qubit numbers. And then, of course, a very active area of research, both in an academic setting, but also from the point of view of many companies, startups, and established ones, is creating quantum computers that are able to solve problems that are currently intractable for classical computers, even the best ones we have. And as you can see, there are really kind of many different platforms that are being approached or used to try and achieve these applications in sensing, networking, and computing. Some of the most well-developed ones for compute are superconducting qubits. There's also, of course, trapped ion-based computers, neutral atom-based computers, photonic quantum computers as well. And for networking and sensing, solid-state spin qubits are often used, as well as, of course, still atom-based and superconducting-based systems. But very generally speaking, regardless of the platform that you kind of choose, one of the big challenges in the field for making useful quantum systems is that you have to grapple with kind of two main requirements that are sometimes at odds with each other. So on the one hand, you want your systems to be scalable, and specifically you want to be able to increase the number of qubits that interact with each other and that are present in the system without introducing excessive sources of noise that can basically hamper your quantum properties and therefore the performance of your quantum system. And at the same time, you want to make sure that in a scalable architecture, you're also able to maintain full controllability, not just of the individual qubits themselves, but also of the interactions between qubits, because you need to preserve high fidelity and low error rates over multi-qubit gates in order to actually do your information processing. And these, in some ways, can be requirements that are sometimes at odds with each other, because on the one hand, you want to totally isolate your qubits from your environment, but you don't want to isolate your qubits so much that it's extremely difficult to control them. So our approach for making these types of quantum technologies has actually been based on a system using semiconductor or insulator qubits that are also optically active. These are spin qubits that exist in materials and occur when, if you get a pristine material, you either eliminate an atom and add an electron, or you substitute an atom with a different element and have also a net charge. And in some of these systems, which are already kind of leading platforms for networking and also for some types of chip-scale quantum sensors, as I mentioned a few slides back, one of the big advantages is that they're in principle compatible with foundry or CMOS fabrication techniques that are intrinsically quite scalable. And so they, while less developed for these applications, they do have promise also for making kind of scalable computers and generally quantum simulators. One thing that's quite similar for all of these qubit types is that their level diagram is usually something like this. So you have a ground state manifold that includes multiple states that depend on the spin state of the actual electron in the color center or defect that you're looking at. And that is where you actually encode your qubit levels, your 0 and 1. These states are often split by relatively low energies on the gigahertz scale, so you can address them with, actually even on the megahertz scale in some cases, so you address them with microwave photons. And then this manifold is also coupled to an excited manifold via an optical transition that you can use for both readout and initialization of the qubit state. So what that means is that you can also integrate these types of qubits into nanophotonic and electronic circuits, which promise to essentially transform some of the bulky free space optics that you see in many quantum experiments in academic but even industrial settings into a fully on-chip integrated structure that you can fabricate at scale. And in addition to kind of this miniaturization and scalability advantage, the other part is that these optical transitions allow you to have this fast control. They're fairly low loss if you have high quality photonics, and you get excellent programmability both from the microwave degree of freedom as well as from other electronic parts of the circuit, which enable control over various properties of the spin qubits themselves. So the type of platform that we're kind of working towards is one where you have these types of spin qubits that are integrated into some nanophotonic resonator such that they can strongly couple to light. You can encode a lot of the spin information or the qubit information into photons and then route them in different directions within the chip via photonic waveguides. The other part of our integrated circuit is, of course, being able to control these photons and, as a result, these interactions between different sets of qubits with some type of photonic switch. And then, of course, you also want to have detectors or waveguides that go into other quantum modules such that you have a scalable architecture. And there are really kind of two requirements that are needed in order to achieve this. The first is you want to have, of course, good qubits. You want to be sure that you have coherent qubits, that they're controllable, and that you can integrate them readily into these types of structures. And the second requirement is you need to ensure that the system has all the required photonic and quantum tunability that you would need in order to fully program interactions between different sets of qubits and also program the qubits themselves. And this is actually kind of somewhat of a challenging obstacle for these types of systems, because oftentimes some of the hosts of the best qubits are just not tunable enough from the photonic perspective. So heterogeneously integrating these systems with additional materials that are more tunable might enable programmability and all the system level tunability that you need, taking advantage of the individual properties of the different materials. So throughout kind of the past years, I've worked actually on both of these requirements. I've done work on various types of solid state qubit systems, ranging from qubits in diamond, like nitrogen vacancy and tin vacancy centers that are commonly used for sensing and quantum networking. We've also worked with silicon vacancy centers in silicon carbide that can be integrated into cavities, as you can see from this image in the center. And you can engineer already interactions between order 10 or more emitters to approach some applications in multi-emitter cavity QED and quantum simulation. And I've also looked at some novel qubit states in two-dimensional materials, specifically boron vacancies in hexagonal boron nitride, where we've already shown that without any surface treatment, we can approach performance of some of the best solid state and V-center qubits in terms of both the sensitivity to magnetic signals and the depth at which the qubit is with respect to a surface. We've also done a lot of photonics work, both in making kind of high quality silicon carbide photonic structures with very low loss and high quality factors in your nanophotonic structures that also include electrical control of either the photonic modes or the qubits integrated in these photonic resonators. And we've used inverse design photonic techniques to create fully monolithic photonic platforms in new materials like HBN, where we are able to create both couplers that are small scale and efficient, as well as mirrors for cavities and resonators in these systems. And lastly, what I'll spend kind of most of the remaining time on is I've also worked on exploring new material systems that are extremely tunable in the photonic realm that can be heterogeneously integrated into these integrated circuits that I mentioned a few slides back. So the specific tunability that we have been looking at in this regime is the so-called electro-optic tunability, which, as you all know, happens when you apply an electric field to the material and are able to change its refractive index. And using this very simple property, one of the things you can do, of course, is a switch or an on-chip modulator, which is a basis for a lot of this controllability that we need in these integrated photonic circuits, and also, as I'll get to, for other quantum applications as well. And of course, you can use the same ideas also to tune resonators themselves. So for example, to make tunable on-chip lasers, but also make tunable spin-photon interfaces for our qubits, and even think of doing some tunable control of far-field optical signals via metasurfaces or other beam steering-like devices. And the reason that we needed to look for electro-optic materials that are new and more tunable is that while there's been a lot of research in this field specifically, this is kind of a nice review by IBM. Most of it is, of course, has been at room temperature, where most applications thus far were necessary. And as you can see, there's a broad range of electro-optic tunability that you can recover from different material systems. This is kind of outlined by the Pockels coefficient, which tells you how much the refractive index is changing upon application of an electric field. And you can see some very common materials, starting from, silicon, gallium arsenide, or silicon oxide, gallium arsenide, lithium niobate, and barium titanate all have very different Pockels coefficient. But one challenge is that for many of these materials, or actually most of these materials, their performance actually degrades as you go to cryogenic temperatures, which is where you want these materials to operate, because you need them to be integrated into nanophotonic circuits, where you also have spin qubits that often require these cold temperatures to have enhanced coherences for your quantum applications. In a way, this is because you're basically going from systems that are close to phase transitions to systems that are farther and farther away from phase transitions. And it turns out that the proximity to phase transition actually gives you a lot of information about how strong the nonlinearity is in these systems. And indeed, if you plot these leading materials at room temperature and their proximity to where they go from a paraelectric to ferroelectric state, you see that the most tunable ones are the ones closest to a phase transition at room temperature. And there is this very nice relationship between these electro-optic nonlinearities, phase transition, and also linear susceptibilities of the system. As a result, if you want to optimize kind of the material specific for an operating temperature, what you want to really do is choose a material that has a phase transition close to that operating temperature. And it turns out that there was a material that has this low temperature transition. It's known as strontium titanate. It's a material that actually has been studied for quite some time in the context of material science and condensed matter. As you can see, even from studies in the late 70s, there were dielectric constant studies that show that there is a sharp increase as you approach low temperatures, and that indicates that the system is close to a paraelectric to ferroelectric transition, but never fully undergoes the transition because it stays in a so-called quantum paraelectric state. And so we've been able to measure via Mach-Zehnder interferometry measurements the electro-optic coefficient of this type of material as a function of a DC bias electric field, which we still need to break the symmetry in the system because it is a Chi-3 system, and the temperature. And what you see is that as you cool from room temperature down to cryogenic temperatures used in quantum experiments, you get a very strong enhancement in the Pockels coefficient, and you also get an enhancement in the piezoelectric coefficient. Respectively, there are around 500 picometers per volt and 100 picocoulombs per newtons, which are the largest reported at cryo, and more than 10x lithium niobate. And it turns out that you can use this intuition that you want to be close to phase transitions to even further improve these optical nonlinearities in the system by moving even closer to a quantum critical point or this phase transition point. One of the ways to do this is actually to substitute the naturally occurring oxygen-16 isotopes with oxygen-18. Again, there's kind of been some research in the context of dielectric constant and other physical properties that has shown indeed this enhancement as you approach around 37% oxygen-18 ratio in the system. And together with our collaborators, this is exactly what we did. We tuned the oxygen-18 ratio in the system to around 33% and saw a drastic enhancement in both the Pockels coefficient and the piezoelectric coefficient to over 1,000 and around 400 actually at some temperatures for our system. And so we really were able to kind of optimize the nonlinearities in the system at these specific cryogenic temperatures, outperforming any kind of known material at this temperature by more than 5 times, and lithium niobate, which is the most used materials, by more than 40 times. And as a brief outlook in the last few minutes that I have, this advancement in better kind of electro-optic materials is useful not just for this heterogeneous
Giovanni,
integration.
the time is already up, by the way.
Oh, the time. Oh, sorry, I missed it. Okay, then the only thing I'll say is that these advancements actually have applications also in other kind of quantum systems, including photonic quantum computing and microwave to optical transduction. And I'll end here thanking my advisor, Jelena, as well as all the other collaborators, specifically groups at University of Michigan.
Great.
Maybe
Thank you, John.
I missed a 2-minute warning.
No worries. Yeah. So we have time for 1 or 2 questions. I don't know if Stefano or Alberto have any.
I have a quick one. You mentioned tuning the refractive index. Is it important to tune only the real part and you don't care about the imaginary, or we want to be able to tune both of them, or what is the criterion there?
Yeah, no, that's a great question. Yeah, in this case, we mostly cared about the real part in terms of imparting phase onto the system. And the imaginary part, you want to be careful how much you're tuning. You don't want to introduce too many losses into the system because in addition to having the large tunability, you also need, of course, the low loss in your photonic circuit. And as a result, we've kind of looked at both. And specifically, we've seen that losses in this system are low enough that they're okay for these applications, especially because you get such a boost from the kind of standard real refractive index tuning.
I enjoyed your discussion on the need for working near the temperature transition and of the phase change. So you found this new material that can enable that. Do you think there are opportunities also for synthesized, like synthetic materials that can be tuned to the right temperature, maybe by combining?
Yeah, that's a great point. Yes, I think, very generally this relationship there is between these electro-optic and even piezoelectric nonlinearities and phase transitions is actually quite general, as I was kind of trying to also discuss by looking at other types of materials. And so indeed, while we basically mostly were looking for materials that had already been studied, just not in this kind of context, there is an opportunity to do additional kind of changes to the materials via doping, for example, with different types of elements, as we saw doping with different types of isotopes, to move even closer to the transition. So you can think of, even in the context of STO, using other group 2 elements and moving even closer, and therefore enhancing the properties. There's also a question of whether you want to be kind of on the right side or the left side, of course, of this transition. And so you can also use these same ideas, making kind of new designer materials to try and be where exactly you want to.
Thank you. I think it's time to close this final. Thank you very much to Giovanni, but also before to Gabriele and to Marco. Great talks. Congratulations again for being selected. And on behalf of the jury, we congratulate all three. We hope that we will see you at the event on November 6th at the Italian Embassy. And I would like to close by introducing the president of ISNAF, Dr. Cinzia Zuffada, that would like to say a few words.
Thank you, Andrea. So let me start by congratulating the finalists, an impressive trio of young investigators. So you will do you are already doing us a great honor for having participated to this year Embassy of Italy Award. I look forward to meeting you in person on November 6th, where we will have a poster session, and we will have the opportunity to celebrate your achievements with the community. And let me thank one more time the jury, Andrea, for shepherding all of this together, and the reviewers and the jurors for their hard work. There is more work ahead in selecting the winner amongst this trio of very strong finalists. And again, the virtual presentation session is coming to an end. You all have a good day, and see you soon in DC.